November 29th, 1944. Over Tokyo, Japan. At 30,000 feet above the sprawling capital, Captain Robert Rodenhouse guided his Boeing B-29 Superfortress through crystalline air so thin it would kill an unprotected man in minutes. Yet, inside his pressurized cockpit, Rodenhouse breathed comfortably, his hands steady on the controls, the cabin pressure maintained at the equivalent of 8,000 feet, despite flying nearly 6 miles above the Earth. Below, Japanese fighter pilots struggled desperately to reach his altitude, their engines gasping in the oxygen-starved stratosphere. This was the first strike against Tokyo from the newly captured Marianas, and it marked the beginning of a strategic bombing campaign that would bring Japan to its knees. But what impressed Japanese observers most profoundly was not the bomb loads, not the defensive firepower, not even the superfortress's intimidating size. It was something invisible, something the enemy could barely comprehend, a technological achievement so far beyond Japanese capabilities. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today, that it would fundamentally alter their understanding of American industrial power. The B-29 could operate routinely at altitudes where Japanese interceptors simply could not reach. And when pilots finally clawed their way up to 30,000 feet, gasping through oxygen masks, fighting to stay conscious in the brutal cold, they found American aircrewmen sitting in pressurized, heated comfort, as relaxed as if they were flying at half that altitude. The Japanese had fighters, they had courage, they had determination, but they had never built pressurized cabins that could sustain crews for 16-hour missions above 30,000 feet. And that technological gap would prove decisive. The story of how Japan confronted this American advantage reveals more than technical disparity. It exposes the chasm between two industrial philosophies, two approaches to manufacturing, two visions of modern warfare. By the time Japanese engineers fully grasped what Boeing had achieved, understanding the principles behind pressurized high-altitude operations, the war was already lost. Not on any battlefield, but in the factories and engineering laboratories where America had mastered technologies Japan could barely imagine. 3 years earlier, in 1941, Boeing engineers had faced what seemed an impossible challenge: create a bomber capable of carrying significant bomb loads across vast Pacific distances while flying high enough to escape most enemy defenses. The distances were staggering. From the Marianas to Tokyo measured 1,500 miles each way. Round trip, 3,000 miles minimum, often extending to 3,600 miles or more, depending on weather and tactical considerations. Mission times routinely exceeded 14 hours. Some approached 16 hours. Flying such distances at low or medium altitude invited disaster. Japanese fighters would swarm any formation within their reach. Anti-aircraft fire would exact terrible tolls. But high altitude presented equally daunting obstacles. At 30,000 feet, outside air temperature plunged to 60 degrees below 0 Fahrenheit. Air pressure dropped to less than 1/3 sea level values. Unprotected humans at such altitudes had perhaps 15 seconds of useful consciousness before hypoxia rendered them helpless. Previous Allied bombers had dealt with these challenges through bulky, uncomfortable solutions. Crewmen wore electrically heated flight suits against the cold. They breathed through uncomfortable oxygen masks that frequently malfunctioned or froze. They endured brutal conditions that exhausted them physically and mentally, degrading performance on missions lasting 6 to 8 hours. For missions lasting 16 hours or more, such primitive solutions simply wouldn't work. Crews would arrive over target too fatigued to bomb accurately, too worn down to defend themselves effectively, too compromised to fly home safely. Boeing's answer was revolutionary. Rather than ask crews to endure the environment, Boeing would bring sea-level conditions into the aircraft. They would pressurize the crew compartments, maintaining breathable atmosphere even at extreme altitude. They would heat those compartments to comfortable temperatures. They would create an environment where crews could work in shirt sleeves, where fatigue would result from mission length rather than environmental stress, where human performance could remain optimal throughout brutally long combat operations. The concept was not entirely new. Boeing's own Model 307 Stratoliner, a commercial airliner developed before the war, had pioneered pressurized flight. But scaling that technology for military application presented extraordinary challenges. The Stratoliner carried passengers in comfort for a few hours. The B-29 needed to maintain pressurization through 16-hour combat missions, while enduring battle damage, extreme temperature variations, and the constant stress of combat operations. The engineering demands were unprecedented. Boeing created 3 separate pressurized compartments within the B-29's fuselage. The forward compartment housed the pilot, co-pilot, flight engineer, bombardier, navigator, and radio operator. The rear compartment contained the central fire control gunner, 2 side gunners, and the radar operator. The tail gunner occupied his own small pressurized compartment in the aircraft's extreme rear. A tunnel connected the forward and rear compartments, allowing crew movement while maintaining pressure integrity. Each compartment required airtight construction using technology that barely existed in 1942. Every rivet hole represented a potential leak. Every access panel, every inspection hatch, every equipment installation threatened the pressure seal. Boeing engineers developed specialized gaskets, unique sealants, and novel construction techniques. They created pressure bulkheads strong enough to contain differential pressures, while light enough not to compromise the aircraft's weight limits. They designed pressure regulators, relief valves, and safety systems that had never been built before. The Wright R3000, 350 duplex Cyclone engines drove the pressurization system through engine-mounted compressors. Bleed air from these compressors flowed through ducting to the crew compartments, maintaining 8 pounds per square inch pressure differential. At 30,000 feet, where outside pressure measured only 4.3 pounds per square inch, the cabin maintained the equivalent of 8,000 feet, 12.2 pounds per square inch. This 7.9 psi differential placed enormous stress on the fuselage structure. The pressurization system had to maintain this differential continuously, compensating for inevitable small leaks, for gun port openings, for pressure fluctuations during climbs and descents. The system heated incoming air to comfortable temperatures using exhaust heat exchangers, creating cabin environments around 70 degrees Fahrenheit, despite outside temperatures 50 below zero. It controlled humidity to prevent frost formation on instruments and windows. It filtered air to remove engine exhaust contaminants. It accomplished all this automatically, without requiring constant crew attention. When the first B-29 flew in September of 1942, it represented the most technologically advanced aircraft ever built. Pressurized crew compartments, remote-controlled gun turrets coordinated by analog computers, radar navigation and bombing systems, 4 of the most powerful piston engines ever installed in a production aircraft, flush-riveted stressed skin construction for reduced drag, massive bomb capacity, extraordinary range. Every system pushed the boundaries of what was technically achievable, but the rushed development schedule created severe problems. On February 18, 1943, the second B-29 prototype crashed during testing, killing Boeing's chief test pilot Eddie Allen and his entire 10-man crew, plus 20 workers in a meat-packing plant when the burning aircraft plowed into the building. The crash resulted from engine fire, a problem that would plague the B-29 throughout its service life. The Wright R3000 350 engines ran so hot that cylinder head temperatures regularly exceeded safe limits, causing oil seal failures, valve problems, and catastrophic engine fires. The pressurization system added its own complications. Sealing the massive fuselage proved extraordinarily difficult. Early production aircraft leaked like sieves, unable to maintain adequate pressure differentials. Gaskets failed, sealants cracked in the extreme cold. Pressure bulkheads developed leaks around rivet lines. Boeing implemented fix after fix, each one adding weight, each one delaying production, each one threatening the entire program. By mid-1944, the B-29 program had cost $3 billion more than the Manhattan Project that would develop the atomic bomb. It was the most expensive military program of World War II. Despite these problems, B-29 seconds began reaching combat units in early 1944. The XX Bomber Command, based in India and staging through bases in China, flew the first combat mission against Japan on June 15, 1944. 68 B-29 seconds attacked the Imperial Iron and Steel Works at Yawata on Kyushu Island. The raid achieved minimal damage but demonstrated that American bombers could now reach the Japanese home islands. For the Japanese military and civilian population, this was a psychological shock of profound magnitude. The Japanese had believed themselves safe. Their island fortress, protected by vast ocean distances and powerful naval and air forces, had seemed invulnerable to strategic attack. The Doolittle raid of April 1942 had been a propaganda stunt. 16 medium bombers launched from an aircraft carrier, incapable of repeating their mission. But the B-29 seconds represented something entirely different. These were heavy bombers operating from established bases, capable of flying repeatedly, of carrying heavy bomb loads across enormous distances, of striking targets throughout the Japanese Empire. And they flew beyond the reach of Japanese defenses. Standard Japanese fighters, the Mitsubishi, a 6M0, the Nakajima Ki-43 Hayabusa, the Kawasaki Ki-61 Hien, could barely reach 25,000 feet, and their performance degraded catastrophically at such altitudes. Their engines, designed for low and medium altitude operations, gasped for air in the thin atmosphere. Their rate of climb dropped to nearly zero. Their maneuverability, their greatest advantage, disappeared in the rarefied air. And even when they somehow clawed up to 30,000 feet, they found themselves facing B-29 seconds that operated comfortably at those heights, defended by remotely controlled gun turrets that could track them with computer-assisted accuracy. Japan had a few high-altitude interceptors. The Mitsubishi J-2M Raiden could reach 38,000 feet, though it performed poorly at extreme altitude. The Kawasaki Ki-84 Hayate, when equipped with properly manufactured engines and operating with quality fuel, could reach the B-29 seconds and engage them effectively. But Japan produced too few of these advanced fighters, and chronic quality control problems meant many never achieved their designed performance. Skilled pilots flying properly, maintained examples could and did shoot down B-29 seconds, sometimes employing desperate ramming attacks when ammunition ran out. But individual heroics couldn't compensate for systematic industrial and technological inferiority. The real advantage the B-29 enjoyed came from that invisible technology pressurization. While Japanese pilots fought through 16-hour missions wearing bulky flight suits, breathing through freezing oxygen masks, enduring brutal cold that numbed fingers and clouded judgment, American crews sat in heated comfort. They could remove oxygen masks when needed to eat or drink. They could work without heavy gloves, maintaining fine motor control for complex tasks. They could concentrate on navigation, bombing, defensive tactics, rather than simple survival. The psychological advantage was immense. The performance advantage was decisive. Japanese technical intelligence services recognized the B-29's pressurization as a critical technology, but understanding a technology and replicating it are entirely different challenges. Japan's aviation industry, despite producing some excellent aircraft designs, operated with fundamental limitations that made matching American achievements impossible. Japanese aircraft production relied heavily on skilled manual labor and traditional manufacturing methods. Individual craftsmen fitted components to specific airframes. Parts from one aircraft rarely fit another without adjustment. Quality control depended on the skill and attention of individual workers, rather than systematic manufacturing precision. This approach worked adequately for producing hundreds of aircraft. It could never scale to produce thousands while maintaining consistent quality and incorporating advanced technologies like pressurization systems. Building a pressurized aircraft required manufacturing precision that Japanese industry had not achieved. Every pressure vessel component must be built to exacting tolerances. Pressure bulkheads must seal perfectly. Every penetration for wiring, hydraulics, or controls must incorporate leak-proof fittings. The fuselage skin itself must be airtight, with every rivet hole properly sealed, every panel joint gasketed, every inspection hatch designed to maintain pressure integrity under extreme stress. This level of systematic precision manufacturing existed in American factories but remained beyond Japan's industrial capabilities. Even if Japanese engineers could design a pressurization system, and they certainly understood the theoretical principles, their manufacturing infrastructure couldn't reliably produce the components. Pressure regulators required precision-machined valves and springs manufactured to tolerances measured in thousandths of an inch. Compressors needed high-quality bearings that could operate continuously for 16 hours under extreme conditions. Ducting required specialized alloys and welding techniques. Seals demanded rubber compounds that remained flexible at 60 below zero while maintaining pressure integrity. American manufacturers produced these components by the thousands with consistent quality. Japanese suppliers struggled to produce even small quantities, and quality varied wildly between batches. A pressure regulator from one production run might work perfectly. The next batch might fail within hours. This inconsistency made it impossible to field pressurized aircraft operationally, even if prototype examples could be built. Japan did attempt high-altitude interceptor development with some pressurization features. The Tachikawa Ki 94II experimental fighter incorporated a primitive pressurized cockpit, but the program never advanced beyond prototype stage. The Mitsubishi Ki 83, another high-altitude fighter project, planned for cockpit pressurization, but never reached production before the war ended. These projects demonstrated Japanese awareness of the technology's importance. They also revealed Japan's inability to implement such systems in operational aircraft. The fundamental issue wasn't knowledge or theoretical understanding. Japanese engineers read the same technical literature as their American counterparts. They understood aerodynamics, thermodynamics, and materials science. Several had studied in the United States or Europe and knew precisely what was technically achievable. But understanding principles and implementing mass production of complex systems are vastly different challenges. Japan's industrial base simply lacked the systematic precision manufacturing capability, the quality control infrastructure, and the supply chain reliability required for such advanced technology. By November of 1944, when the first B-29 raid hit Tokyo from the Marianas, Japanese industry was already failing. American submarine warfare had severed supply lines, cutting off raw materials from conquered territories. Strategic bombing targeted key industrial facilities. Skilled workers were being drafted into military service. Quality declined as inexperienced workers replaced craftsmen. Production numbers fell despite desperate efforts to increase output. In March of 1945, General Curtis LeMay changed B-29 tactics dramatically. Instead of high-altitude precision bombing, his forces would conduct low-altitude incendiary raids. The massive fire raid against Tokyo on March 9th and 10th killed an estimated 100,000 people, destroyed 16 square miles of the city, and demonstrated that Japanese defenses could not protect the homeland. LeMay stripped defensive armament from many B-29 seconds to increase bomb loads, gambling that Japanese defenses were so weak that the heavily armed superfortresses no longer needed full firepower. The gamble succeeded. Japanese fighter opposition had been ground down through months of attrition, fuel shortages, limited training and operations. Experienced pilots had been killed faster than replacements could be trained. The few remaining high-performance fighters often couldn't fly due to lack of fuel or spare parts. Anti-aircraft ammunition ran short. The systematic degradation of Japanese defensive capability meant that by April of 1945, B-29 seconds operated over Japan with near impunity. The pressurization technology that had seemed so critical in November of 1944 became less tactically important as B-29 seconds shifted to low-altitude operations. But the underlying message remained devastating. America possessed industrial capabilities that Japan could not match. The pressurization systems represented visible proof of systematic manufacturing precision, of engineering sophistication, of industrial organization that produced complex technology reliably and in vast quantities. Japan's inability to field similar technology revealed fundamental weaknesses in its industrial structure. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. It wasn't that individual Japanese engineers or workers were less skilled than their American counterparts. Many were highly skilled, highly educated, highly motivated. But modern industrial warfare isn't won by individual skill. It's won by systematic organization, by precision manufacturing at scale, by supply chains that deliver consistent quality components, by industrial processes that build complexity into the production system itself, rather than relying on craftsmanship to correct defects. The B-29 program built 3,970 superfortresses between 1943 and 1946. Each one incorporated pressurized crew compartments built to consistent standards. Each one could fly 16-hour missions at 30,000 feet, with crews operating in comfort. Each one represented American industrial organization at its peak complex technology, mass-produced with consistent quality through systematic manufacturing processes. By May of 1945, the strategic bombing campaign had destroyed much of Japan's industrial capacity. The Nakajima plant at Musashino, producing aircraft engines, lay in ruins. Mitsubishi's facilities at Nagoya had suffered severe damage. Kawasaki's factories were devastated. An earthquake in January compounded the destruction. Monthly aircraft production, which had peaked at over 2,500 airframes in May of 1944, collapsed to barely 1,500 by early 1945 and continued falling. The pressurization advantage the B-29 enjoyed was never about just the technology itself. It was about what that technology revealed. An aircraft with pressurized crew compartments required systematic precision manufacturing. It required reliable supply chains delivering consistent quality components. It required engineering processes that designed for mass production from the beginning. It required quality control systems built into production rather than relying on inspection to catch defects. It required industrial organization fundamentally different from Japan's craftsman-based approach. When the war ended in August of 1945, American technical teams swept through Japan documenting industrial capabilities. The United States Strategic Bombing Survey conducted comprehensive examinations of Japanese factories and production methods. What they found confirmed what perceptive Japanese engineers had long understood. Japanese aviation manufacturing was organized appropriately for producing hundreds of aircraft. American factories were organized for producing hundreds of thousands. American engineers touring Mitsubishi facilities at Nagoya observed skilled craftsmen hand-forming aluminum panels that would have been die-stamped in American factories. Manual riveting predominated, where American factories used automated riveters. Individual fitting and adjustment were common, where American production used precision-manufactured interchangeable parts. The survey concluded that no amount of determination or skill could overcome the fundamental disparity in industrial organization. After Japan's surrender, the country faced the task of rebuilding from ruins. Engineers and technical specialists who had observed American aircraft and American production methods during the war brought those lessons to reconstruction efforts. They understood that matching American industrial capability required not just copying American products, but implementing American production systems. The transformation took decades. Japanese factories that had relied on skilled craftsmen reorganized around precision machinery and automated processes. Industries that had valued individual craftsmanship learned to value systematic efficiency. Manufacturing evolved from collections of skilled workers into integrated production systems. By the mid-1960s, Japanese factories were producing automobiles and electronics, using automated production methods comparable to American factories. By the 1970s, Japanese manufacturers had refined those methods, developing production systems like Toyota's just-in-time manufacturing that improved on American mass production techniques. The skilled craftsmen remained valued in Japanese industry, but their role changed. Instead of individually crafting products, They designed production systems and tooling that enabled less skilled workers to produce precisely manufactured products at scale. The precision that had once come from craftsman skill now came from the precision of tooling and equipment. Companies like Toyota, Sony, and Honda became global leaders by combining Japanese attention to detail with American systematic production methods. The irony was profound. In the 1980s, when American manufacturers faced intense competition from Japanese imports, American engineers toured Japanese factories to learn efficiency techniques. The industrial roles had reversed. Japan had learned the lesson the B-29 taught. Modern industrial competition is won not by superior craftsmanship, but by superior production systems, not by building better individual products, but by building adequate products in overwhelming quantities using systematic processes. The story of the B-29's pressurized cabins became a case study in Japanese engineering schools. It illustrated how examining an opponent's products could reveal fundamental principles of industrial organization. It demonstrated that success required understanding not just what competitors produced, but how they produced it. The B-29 had taught Japanese engineers that modern industrial warfare was won by production systems, not by individual excellence. Those lessons learned through observing American equipment during wartime became the foundation for Japan's post-war industrial success. The transformation of Japanese manufacturing from craftsman-based production to systematic mass production represented the final victory of the principles embodied in those B-29 seconds that flew over Japan. The engineers who had recognized American manufacturing superiority in the B-29's sophisticated systems became architects of Japan's industrial rebirth. Boeing built the B-29 to win a war through strategic bombing. It accomplished that mission. But perhaps the bomber's most important contribution to history wasn't the missions it flew or the targets it destroyed. It was the lesson it taught about industrial organization and systematic manufacturing. The pressurization systems that allowed crews to operate in comfort at 30,000 feet were merely the visible manifestation of invisible industrial capabilities. Precision manufacturing, systematic quality control, integrated supply chains, and production processes designed for mass manufacturing of complex technology. The Japanese engineers and observers who watched B-29 seconds flying beyond the reach of their defenses understood that American industrial power came not from superior materials or revolutionary designs, but from superior organization of the manufacturing process. They learned that standardization, precision tooling, interchangeable parts, and systematic production methods could achieve what skilled craftsmanship alone could not. The ability to produce complex machines rapidly and in quantities limited only by available resources. The B-29 seconds that appeared over Japan in 1944 delivered more than bombs. They delivered a message about industrial capability, about manufacturing precision, about systematic organization. That message, read and understood by perceptive Japanese engineers, ultimately shaped Japan's post-war transformation into an industrial powerhouse. The crews who flew those long missions barely thought about the pressurization systems that kept them comfortable at 30,000 feet. The technology was there. It worked. It allowed them to do their jobs. But to observers on the ground, to engineers trying to understand how America had achieved such capability, the pressurization represented something profound, proof that American industry had mastered technologies and production methods that Japan could not match. When the B-29 Enola Gay dropped the first atomic bomb on Hiroshima on August 6, 1945, it flew at 31,000 feet, its crew working in pressurized comfort. 3 days later, Bockscar delivered the second atomic bomb to Nagasaki from similar altitude. These missions ended the war and demonstrated the ultimate expression of American technological superiority. But they also represented the culmination of systematic industrial achievement, the ability to design, develop, and deploy the most advanced technologies through organized mass production. The pressurized cabins that allowed B-29 crews to operate effectively on 16-hour missions at extreme altitude were never just about crew comfort. They were about what that technology revealed. American industry's capacity to master complex engineering challenges, to implement advanced systems in production aircraft, to maintain quality and reliability across thousands of units. That capability, more than any specific weapon or technology, determined the war's outcome. The final lesson of the B-29's pressurized cabins is that in modern industrial warfare, victory belongs not to those with the bravest soldiers or the most skilled craftsmen, but to those with the most effective production systems. Japan learned that lesson the hard way, watching American bombers fly beyond their reach, demonstrating capabilities Japanese industry could not replicate. In learning that lesson, Japan ultimately transformed itself, applying those principles to become an industrial leader in the post-war world. The bombers are gone now, most scrapped decades ago. Only two B-29 seconds still fly FIFI and dock, preserved and maintained by dedicated volunteers. But the lessons those aircraft taught continue to shape manufacturing worldwide. Modern production methods, whether building aircraft or automobiles or electronics, reflect principles the B-29 embodied. Systematic precision, integrated processes, quality designed into manufacturing rather than inspected in afterward. The Japanese engineers who observed B-29 seconds operating at 30,000 feet, who understood that pressurization represented systematic manufacturing capability they could not match, helped build the industrial Japan that emerged from war's ruins. They learned that the battle was never really about individual technologies. It was about industrial organization, about production systems, about the ability to implement complexity at scale. The B-29 taught that lesson better than any textbook could, and Japan, in defeat, learned it well enough to ultimately become a global manufacturing leader. The strategic implications of pressurization technology extended far beyond crew comfort or operational altitude. When Boeing engineers designed the B-29's pressurization system, they created a competitive advantage that compounded across every aspect of bomber operations. A crew flying in shirt sleeves at comfortable cabin pressure could concentrate on complex tasks that exhausted crews in unpressurized aircraft. Navigation became more precise when navigators weren't fighting hypoxia and cold. Bombing accuracy improved when bombardiers could work with steady hands and clear minds. Defensive gunnery proved more effective when gunners maintained full cognitive function throughout 16-hour missions. Japanese interceptor pilots, struggling to reach 30,000 feet in aircraft designed for lower altitudes, arrived at engagement altitude already exhausted from the climb. Their oxygen masks froze, restricting breathing, their hands numbed in the brutal cold, making precise control difficult. Their minds worked slowly, reaction times degraded by hypoxia despite supplemental oxygen. They faced American gunners who sat in heated compartments, breathing normally, operating complex fire control systems with full mental acuity. The physiological advantage was crushing. This reality became apparent to Japanese pilots early in the B-29 campaign. Flight Sergeant Isamu Sasaki of the 244th Sentai described the desperate struggle to intercept superfortresses in early 1945. His Ki-84 Hayate, one of Japan's best fighters, could theoretically reach 35,000 feet, but the climb to intercept altitude took nearly 30 minutes, burning precious fuel, leaving him gasping despite his oxygen mask. By the time he reached the bomber's altitude, his ammunition load gave him perhaps 2 passes before he had to break off and descend. The Americans, meanwhile, had been flying comfortably for hours and would continue flying comfortably for hours more. The psychological impact on Japanese defenders was profound. They weren't just fighting a technologically superior enemy. They were fighting an enemy that operated in apparent ease, while Japanese pilots endured brutal physical stress. The B-29 crews could eat meals during missions, drink coffee, move freely between pressurized compartments. Japanese pilots flew in frozen cockpits, unable to remove oxygen masks, fighting constant physical discomfort that drained energy and degraded performance. The message was clear. America possessed not just better technology, but fundamentally different approaches to aviation that made such technology possible. Japanese aviation engineers understood the theoretical principles behind pressurization. Several had studied American technical publications describing cabin pressure systems. Some had examined German high-altitude fighter prototypes that incorporated primitive cockpit pressurization. The knowledge existed, but knowledge without industrial capability to implement it at scale meant nothing. Japan could build prototype pressurized aircraft in experimental facilities. They could never manufacture pressurization systems reliably enough for operational deployment across hundreds or thousands of aircraft. The reliability issue was critical. A pressurization system that worked perfectly in 10 test aircraft but failed randomly in operational service was worse than no pressurization at all. Crew members relying on pressurization who experienced sudden decompression at 30,000 feet would be incapacitated within seconds, probably killing them and certainly dooming the aircraft. American pressurization systems, while not perfect, achieved sufficient reliability for operational use. Japanese manufacturing simply couldn't produce components with consistent enough quality to achieve similar reliability. This manufacturing quality gap extended to virtually every advanced system. The analog computers controlling B-29 defensive fire represented another technology. Japan understood theoretically, but couldn't implement practically. Each B-29 carried 5 General Electric analog computers that calculated ballistic corrections, compensating for airspeed, altitude, temperature, target motion, and parallax between gun sight and turret positions. These computers allowed gunners to engage targets accurately at long range, creating defensive zones that forced Japanese fighters to attack through murderous crossfire. Japanese engineers examined these systems through intelligence reports and through examination of crashed B-29 seconds. They understood the mathematics, the mechanical principles, the electrical circuits. But building analog computers that functioned reliably in combat conditions, that could be manufactured in quantity, that could be maintained by average technicians rather than specialists, this required industrial capabilities Japan lacked. The precision machining, the quality control, the systematic testing and refinement necessary to field such systems operationally remained beyond Japanese manufacturing capacity. The pattern repeated across every advanced B-29 system. Remote-controlled gun turrets eliminated the need for individual gunners at each position, saving weight and improving aerodynamics. But the motors, the control systems, the electrical components required for remote turret operation all demanded manufacturing precision Japanese industry hadn't achieved. The central fire control system that allowed one gunner to control multiple turrets required electrical components manufactured to tolerances Japanese suppliers couldn't consistently meet. Each system individually represented achievable technology. Collectively, they revealed a massive gap in industrial organization and manufacturing capability. When American bombing intensified in spring of 1945, Japanese industry was collapsing. The submarine blockade had severed raw material supplies. Strategic bombing destroyed key facilities. Transportation networks failed under sustained attack. Skilled workers disappeared into military service or died in bombing raids. Quality control broke down as desperate managers pushed for quantity over quality. Production numbers meant nothing when half the aircraft coming off production lines had serious defects, requiring extensive rework before they could fly. By July of 1945, Japanese aircraft production had fallen to a few hundred airframes per month, most of them obsolete designs using materials and components scrounged from wherever they could be found. Aluminum shortages forced increasing use of wood and fabric in aircraft that should have been all metal. Engine production collapsed when precision machining facilities were destroyed. Many completed airframes sat on factory grounds awaiting engines that would never arrive. The industrial base that should have been producing advanced fighters to counter the B-29 threat was instead struggling to produce any aircraft at all. The cruel irony was that Japan possessed talented engineers who understood what needed to be done. They knew their manufacturing processes needed systematic reform. They recognized that craftsman-based production couldn't compete with precision mass manufacturing. They saw clearly that American industrial organization represented a superior approach to modern manufacturing, but changing an entire industrial system during wartime proved impossible. The infrastructure didn't exist, the machine tools weren't available, the supply chains couldn't deliver consistent quality materials, the workforce lacked training in mass production methods, and most critically, there was no time. The war was lost before reforms could be implemented. In the final weeks before surrender, Japan had approximately 5,000 aircraft, including trainers modified for kamikaze attacks. These represented Japan's last reserves for defending against the planned Allied invasion, but fewer than half were operational. Fuel shortages grounded most of the remainder. Pilot training had degraded so severely that many pilots could barely take off and land, let alone engage in combat. The systematic collapse of Japanese military capability was nearly complete. Against this backdrop of industrial failure and military collapse, the B-29 represented everything Japan had tried to achieve and couldn't. High-altitude capability, long range, heavy bomb loads, advanced fire control, reliable engines, and most visibly, pressurized crew compartments that allowed sustained operations at altitudes Japanese fighters struggled to reach, even briefly. The bomber embodied systematic manufacturing excellence, industrial organization optimized for mass production of complex technology, supply chains delivering consistent quality components, and engineering processes that designed for reliability from the beginning, rather than hoping to achieve it through skilled assembly. The atomic bombs dropped by B-29 seconds in August of 1945 ended the war abruptly, but conventional bombing had already devastated Japan's industrial capacity and civilian morale. The 66 major Japanese cities attacked by B-29 seconds had suffered catastrophic damage. Industrial production had collapsed, transportation was paralyzed, food distribution networks had failed, urban populations were starving. The systematic destruction delivered by B-29 operations had made Japanese defeat inevitable. The pressurization systems that had seemed so remarkable when B-29 seconds first appeared over Japan in 1944 had become just one more example of American technological superiority. By war's end, Japanese observers understood that the real gap wasn't in specific technologies but in the industrial systems that produced them. America had created manufacturing infrastructure capable of building extremely complex weapons reliably and in vast quantities. Japan had never achieved that capability and couldn't develop it during wartime. This understanding shaped Japan's post-war reconstruction profoundly. Industrial leaders recognized that competing in modern manufacturing required adopting American production methods wholesale, not just copying American products, but implementing American approaches to quality control, standardization, systematic process design, and continuous improvement. The transformation would take decades, but it was built on lessons learned the hard way during the war, lessons taught by B-29 seconds flying beyond reach, demonstrating capabilities Japanese industry could not match. The engineers and technical specialists who had observed American equipment during the war became key figures in post-war reconstruction. They had seen firsthand the difference between craftsman-based manufacturing and systematic mass production. They understood that modern industrial competition rewarded systematic organization over individual skill, and they were determined that Japan would never again fall behind in industrial capability. The B-29, symbol of defeat, became a teacher whose lessons shaped Japan's emergence as a manufacturing superpower in the decades that followed. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.